So, hello everyone. As for the task one, we begin by cleaning and preparing the time series dataset of retail sales for beer, wine, and liquor stores in the US. So, the first, we import approximately 400 data observation into Minitab. The second, we convert the data variable into date or time format and formatted the cell variable YT as a numeric. We sort everything chronologically and confirm that there are no missing values. So, therefore, the dataset is fully ready for further regression and forecast analysis. So, as for the statistical summary of YT, my comment is as for the mean and the median value, which suggests the cell have been increasing over time. As for the minimum and maximum values, that shows a large fluctuation driven by seasonal events like holidays. We also have a high standard deviation, meaning that the demand is unstable and seasonal. So to check the normality distribution, we conduct the Anderson-Darling test and create a normal probability plot. So the p-value is less than 0.005. So we reject the hypothesis that YT follows a normal distribution. The probability plot also shows strong deviation in both tails. This means forecasting model should not rely on normality assumption. So although none of the test distribution perfectly fit the data, but the Weibo provide the best relative fit because it's captured the right skewed and even event dry natural alcohol retail demand. Therefore, Weibo is selected at the most appropriate probability distribution for YT.
So let's continue with test 2. First, we have to analyze the time series patterns. So when you look at the graph, you can see that the series clearly exhibit the trend in the seasonalities. So about the trend, you can see that YT increased steadily from around 1,500 to 8,000 at the end. And it have the smooth upward movements. And about the seasonality, it's repeating 12 months and it have the sawtooth patterns. In contrast, we see some slope changes, but we don't have enough evidence to confirm the long-term cycle. So based on the trend and the seasonality, we believe that seasonal exponential smoothing, classical seasonal decompositions, and the seasonal ARIMA is three methods that are suitable for this data. But we think that whole winter exponential smoothing and seasonal ARIMA is better than classical decompositions. Why we say so? So whole winter outperform classical decompositions because it does not assume a fixed seasonal pattern, and the seasonal ARIMA is more flexible than classical decompositions. So we calculate the forecast value using the whole winter exponential smoothing. It is the result. You can see the forecast of the period 405 and the plot and the residual plot. And this one is the forecast result of the seasonal ARIMA. You can see the forecast here, the model summary and the time series plots. So we have to choose for the best method. So we compare the MSD of the ARIMA and the whole winter. So you can see that the MSD of ARIMA is smaller than the MSD of whole winter. So that means ARIMA can produce forecasts that are closer to the actual observed value. So we think that ARIMA is the best method. So we will forecast the value for 3 periods using ARIMA methods. So you can see the forecast value from the time periods 404. And one more thing, is it possible to check the confidence interval? So yes, actually, in Minitab we actually include the 95% confidence interval by default. So at the lower and the upper limits. So of course, the predicted value can be checked directly against this interval.
And now I will answer question A, analyze the characteristic of the time series data from test 4. As can be seen from the plot shows a strong upward trend from 1992 to 2025, as the sales increase from around 1,000 to nearly 8,000. Furthermore, the plot also shows a repeating peaks and trough at regular intervals, approximately every 12 months, which indicate a strong seasonal variation. The variance also grows with time, and which is typical for non-stationary data. The seasonal fluctuations grows as the level of the series increase. This suggests a multiplicative seasonality. The presence of trend and changing variance means that the series is non-stationary. Based on the original time series plot, the data shows a clear, strong upward trend. Therefore, the first differencing is needed to remove the trend component. The ACF of the original data has strong spikes at lags 12, 24, and 36, which are much higher than the other spikes. The pattern also shows repeating peaks trough every 12 months, meaning the data has strong seasonality. Because of this, we also clear seasonality with period 12 by using seasonal differencing, which is the capital D equal 1. After applying the first differencing, the ACF shows a large spike at lag 1, which is bigger than the other lags in the same year. This suggests that we should use moving average of order 1 term. We also see large spikes at lag 12, 24, and 36, which means the seasonal pattern is still strong. Therefore, we should add a seasonal moving average of order 1 term. From the PACF, after the first differencing, we see that lag 1 is the strong spike, and this supports that we should use autoregressive of order 1 term. There's also a spike lag at lag 12, but the later lag stayed outside the confidence interval and slowly tail off. This means the seasonal part does not show a clear cutoff. Because of this, we choose seasonal autoregressive of 0 order for the seasonal autoregressive components. And from the analysis above, the final selected model is shown on this slide. And as can be seen from the table, all p-values is nearly 0, which is much smaller than 0.05, and this indicates that all parameters are statistically significant. Furthermore, the iteration table also shows that SSE converging, which indicates that estimation is stable.
So here we have the upper equation. It is the full ARIMA equation in its general form, and the below one is the same equation with its values plugged in. We'll come to the young box test before seasonal adjustment. It shows that the p-values is 0, which is smaller than 0.05, so we can conclude that the residuals are not white noise initially. And after adding seasonal differencing and SMA 12, the residual ACF PACF show all autocorrelation are within significant bounds, and there is no clear pattern, so residuals can be considered as white noise. And the residual plots indicate approximate normality and independence. In conclusion, this model is good for forecasting after seasonal adjustment. Next, we'll come to the forecasting for the next 5 periods with the ARIMA model. For the normal probability plot, residual roughly follow a straight line, which approximates normality. For the histogram, it is symmetric around 0. It supports normality assumption. For the residual and fit versus fit and order, there's no clear pattern, so it indicates independence. Last, for the ACF and PACF of residuals, all autocorrelation are within significant bounds, which residuals behave like white noises. In conclusion, this ARIMA model is adequate for forecasting. From the table, we can see that the trend forecast generally increase and consistent with historical upward trend. For seasonality, notice the spike at period 408. It is likely a seasonal peak. On confidence intervals, wider intervals for later periods. And there's a drop at period 409. The forecast seems to decrease sharply, and it should indicate the seasonal trough after peak. Welcome to the visual confirmation. The time series plot with forecast show red point for forecasted values, a 95% confidence band around the forecast, and the continuation of trend and seasonal pattern. Thank you for listening.